We'll start with Michele Migliore from CNR. And the issue today is to explain how the brain simulation platform and eBrains, which is the future infrastructure for brain simulation of HBP, work. Okay, so Michele, please, to you.
Okay. Thank you, Egidio. Thank you for inviting me to this very nice hackathon. I'm going to talk about two things, because we are, as you already know, we are in the middle of a transition between SGA2, what is called SGA2 and SGA3 of the Human Brain Project. For those of you who are not aware of these acronyms, it means that we are changing phase from a phase which has lasted for 7 years to the last phase of the Human Brain Project as a European project called SGA3, and eventually it will become a European research infrastructure. In the last 3 years, in these last 3 years, there are going to be a lot of changes. Many changes in the scientific projects. Well, I'm not going into the details of that. But when we talk about the platform, which is going to be the platform which will be available for everybody outside the Human Brain Project, and in Europe, actually, it is targeted to become the European research infrastructure for neuroscience, you will see some changes with respect to what is now the platform, what we call the brain simulation platform. In general, the brain simulation platform as it is now, it is something that is already working and present several robust and high-level ITRL use cases, which means that you can go to the platform and start doing your science job using the tools and services and use cases that we have already put on the platform. And these eventually will be incorporated or integrated into what it is called the eBrains, which is going to be the new infrastructure. So let me give you some introduction to the eBrains first. As you see, eBrains is coming soon, which means that it is starting building on April the 1st in 2020. And will hopefully be complete in 3 years. Okay, so don't expect to work with this platform today or tomorrow. Eventually you will get an improved platform which will be able to connect among the different platforms that you will be hearing or you already have discussed in these days, which are basically the brain simulation platform, the neurorobotic platform, the neuromorphic, and the HPAC, which is the HPC systems, the supercomputers. Also, in addition to the other platforms that deals with data. Okay, but I'm going to talk about the platform that deals with computational stuff. However, there is something already here, and let me give you, I'm just trying to navigate now the internet. If you are not been already navigating this site, you can go there, begin to navigate it. Internet, okay, here it is. And so here there is find data and share data for the data part, brain atlases, of course, and simulation. This is where I'm going to talk about today. At this point in this new platform, it is just a placeholder for links to something that, for example, now there is the virtual brain already. We're going to put in the following days the brain simulation platform next to this. And, but they are just links to what is the current brain simulation platform that I'm going to show you in the second part of the talk. Since this is a highly interactive workshop, I expect you to stop me every time you don't understand or you have problems or you want to add some comments on what I'm going to show you for the platform working. Okay, so the e-brains, and in particular the part that is dealing with the computational platform, is under what it will be the work package 5 of the Human Brain Project SJ3, which is called eBrains Modeling Services. The leader is Yannis Ioannidis from Athens, and it is called Service Category 3. So no, I'm not going to go into the details of all the new terminology that we are going to use in SJ3. But the name service category will already give you some idea of what we do in this block of the platform. And this in particular is brain modeling and simulation workflows, integrating tools to create and investigate models of the brain at different levels. And what are these levels? So the WPP5, I don't know if you can read it, more or less. The WPP5 is, of course, has many tasks, but you will see these letters here, service category 3 and 4. Service category 3 is for detailed molecular subcellular level description, plasticity models, subcellular pathways of synaptic transmission of synaptic plasticity and things like that. Detailed cellular model description, this is the part in which I'm mostly involved, which deals with the single neurons and cellular level networks. Spiking network level description, this is from Ulick with the NEST mainly, but also PINE and all the spiking neuron description of network and neurons. Whole brain, and I guess you are going to have a session on this, right, Egidio? Yes, absolutely. Yeah. Whole brain, where we try to put everything together, assuming that each region can be modeled as a black box, but of course with all the details that are coming from the previous level of description, the cellular level and the molecular and so on. And then some middleware. There is also a call that is going on for Arbor, which is a new way to model detailed circuit, but in the general purpose simulation. I don't know if Ben is going to talk about this during the hackathon. You are, oh yeah, okay. And then there is, of course, analysis and validation, visualization, neurorobotics, backend. This is now service component 4. And Egidio Falotico, I think, is going to talk about this. I don't know if Egidio is here. And then some technical coordination and things that make all the platform look the same to the users. I'm going to now to show some technical stuff on the structure of these service components, because it gives you the idea of what we are going to be in 3 years from now. And then in the second part of the talk, I'm going to go into more details, explaining what it is now on the brain simulation platform and what you can do with it. And I guess that in some of the hands-on sessions or the tutorial, you are going to use some of the features that are already in the platform. If any of you does not already have a Human Brain Project account, which is needed to enter the platform, please send an email to support in such a way that we can support at humanbrainproject.eu in such a way that we can give you an account on the fly. Okay, the overview of the service component 3, which is the modeling services, is, as you can imagine, the same over the years. Okay, so you have a model creation, simulation, analysis, visualization, comparison with data, and eventually suggest new experiment or suggest new behavior experiment. So this is the classical loop that any modeler would like to do in implementing a model. You start with your concept, or you start from the data, you build a model, you run the model, run the simulation, analyze the data, and then say, okay, this does not look as the experiments. let's see what I'm doing wrong, or I'm sure that my model is good, let's go to the experimentalists and tell them to do this kind of experiment, or, and this is a much more complicated issue, tell them that their experiments are wrong. This is usually not accepted by experimentalists, but it happens that they did something, or they do, or they didn't say you one specific constraint, and then the model goes wrong and nobody knows why, etc. But this loop is a very generic loop, valid for any kind of model. And so in the service component tree, in this component and in the platform, there are different tools that are already deployed on the platform or on the supercomputers, so you can access them directly from the platform or from outside. I'm going to go into a little more details about this because it is a cellular level simulation in which I'm more involved. And you see here that there are 3 levels of access to the platform. I'm talking about general here structure of the platform, but we are going to go deeper in the next part, in the following part of the talk. There are 3 levels. One is the learner, the user, and the other one is the user, and the top level is the expert. So I'm sure that this is an hackathon, so most of you are at the expert level. You don't need any fancy GUI to work. You just want access to the HPC systems with the tools installed, so we can do whatever you want with your code. Okay. However, you see here and also in other communities, the hippocampus and so on, top level, what they're called power users, are very few. There is not a large community of power users because it is something that you accumulate with experience over the years. And so instead, what the EU is asking the Human Brain Project to do is to get users, increase the number of users. They don't care about power users, they care about the number of users. And when we talk about the number of users, we developers, we need to keep in mind that most of the users comes from students and low-level beginners, either experimentalists that would like to do some very simple modeling, or students during course, or students at the university, or beginners, expert experimentalists that would like to test their results with a model. And so that is our target for the developing of the platform. Okay? We cannot go after power users because power users go on their own, and they are very few. But a MOOC course, if you don't know what a MOOC is the massive online course in which you can have thousands of students. We already have organized 2 MOOCs, the BBP has organized it, and these MOOCs on the computational neuroscience have been and are linked to many use cases that are in the brain simulation platform. So this is where we get a lot of users. And when you build something, if you want to get involved with the Human Brain Project on the technical level, on the platform level, you should always keep in mind that your target is the low-level user. Okay, so you need to put some nice graphical interface. You need to take into account any possibility for the user to just point and click and break your code. This is always a possibility, and you need to take care of this. Take into account. So in the simulation at the cellular level, there are going to be these 3 levels. One is directly entering through the use case specific user interfaces, and the other one is for very specific workflow for intermediate users. Those are people that they know what they are doing, basically, both from scientific and technical point of view. They have programming skills. So in general, these use cases are, in contrast to the learner, the front end, in which you will see web interface, basically, web applications, in which you point and click to get your results. Use case-specific workflows are usually implemented in Jupyter notebooks, and this will allow a much higher flexibility in how you control not only your own code, but you can collaborate with other scientists in your lab or with collaborating with the outside lab using the same set of programs. And finally, there is the expert level in which you actually just SSH, open a terminal with in a supercomputer and launch your simulation, which can be either an optimization, and I guess Werner is going to talk to you about in more details about how to do simulation in the optimizations, but also large-scale modelings of hippocampus, or in this case the cerebellum, and all the necessary circuits. Of course, in order to have this kind of organization, we also need a deployment task. And the deployment task makes sure that every time something is changed along the chain, everything gets updated in a way which is transparent to you. Because, I don't know, I mean, many of you, again, have done some coding, and now, for example, we are in the middle of going from Python 2 to Python 3. Of course, all the use cases up to now, over these 7 years, are in Python 2. So we had to change and rewrite part of the coding, or the codes, to be consistent with the compatible with Python 3. But also, we are, as a human brain project, you can have access, and I will explain it later, to several supercomputer systems, which are CSCS in Switzerland, the Cineca in Italy, the Eureka machine in Jülich, and well, this is it, actually. There are 3 supercomputers which, through the project called ICI and the Phoenix infrastructure, which allow you to ask for computer time, an allocation which you can use for doing your own simulation on supercomputers. Well, you keep in mind that among the 3 supercomputer centers, basically each month, any of these supercomputers will have an update, okay? And an update, let's say, based on experience, 30% of the time generates some incompatibility with our code. And so the system does not work anymore. You cannot run on supercomputers anymore your use case because the supercomputer is not compiling and running your code. And so we have to go there and keep trying every day, be sure that everything is consistent, updated, and ready to use by the user. Okay, so then simulation at the whole level. Once you, I mean, the general organization is going to be always the same. You have a front end, you have some inner codes that does whatever you want, and the HPC systems, okay? In this case, the simulation of the whole brain, I'm not going through, of course, the service component. I'm just selecting a few examples. And one which is relevant to this hackathon is the simulation of the whole brain level. Here, the situation is much more complicated because you have a multi-simulator interaction. Of course, I'm talking here about the e-brains. This is something that will come alive not earlier than 2 years from now. I don't expect any results on there are some initial results of co-simulation, means running a code which is running a model which is implemented part in the virtual brain, for example, and part in a nest, and but it is not open to the public yet. I don't think so, but maybe someone can prove me wrong. So these are still to come, but this is the idea. You have a model running on, according to the pieces, running on different simulators, Arbor, Neuron, Nest, Pine, or whatever, and they run together into to form a large model that can simulate a large, I wouldn't say the whole brain, but a large part of the brain, or anyway many regions put together. And this is a more specific view of the multi-simulator interaction and workflow. So you see simulation 1, 2, 3, Arbor, neural nest, and there is everything, and it's tied together in such a way that the user see only the end result in a consistent way, and could be analyzed and visualized, hopefully, in a nice way, through the web, through the platform. Okay, so far there has been a lot of technical problems in doing all the steps through the platform. They could be done individually outside the platform, but eventually what we want to reach is a point, and I think this is very important because it's a unique point for the entire world. The point is that you have a platform in which you can run and do science without the need of installing, downloading and installing anything. You know how painful it is to download and install a larger piece of software which has a lot of dependencies. You need to install here and that. It doesn't work. The Windows machine has some problems. The Unix machine has some problems. We want to avoid everything. We want the user enter the platform and do everything on the platform, including, and this has been the most difficult so far, the visualization of large-scale models. And just to give you a more detailed view of why it has been difficult to, actually impossible, to do visualization from the platform in an efficient way, of course, is that when you have a visualization, when you want to run a visualization of a large system, you need to run on a parallel supercomputer, let's say using a set of GPUs or a set of hundreds of nodes. And this, of course, has to be done on the computing nodes of the supercomputers, which are usually, in all cases, they are not connected to the internet. So you cannot have a web browser directly connected to the computing nodes. And so you have to go through an additional layer of software that does the interface between the computing node of the supercomputer system and your web browser. This has been a major technical problem so far in terms of efficiency in showing visualization. I have up to 10, right? Gideon, up to 10, yeah. Okay, so then next there is analysis and validation workflow of activity data. This also is going based on NEO, and it goes around the elephant. Sonja Grun is the PI on this. Visualization of modeling of simulation. There is a group led by Benjamin Wires that is trying to solve this problem with visualization. But let me go to the brain simulation platform as it is now. So even now you can enter the platform and run your own simulations and your own models. I assume that you already have the Human Brain Project account, but if you don't have it, just send an email here. Okay, from a technical point of view, since this is an hackathon, I cannot go and show you very simple use cases for beginners. But one of the useful things that the reviewers have praised in the last review report is what we call a service account. Okay? Service account is already operative, in operation, thanks to the CSCS, which provide the account, and to Cineca, which provide a virtual machine on which the software runs. The service account is an extremely useful feature because I'm sure that you have been through the process of asking for an account on a supercomputer systems. They send you the form to sign, they want your picture ID sent, they want SSK keys generated, and so on. It is a complex, not complex, but bothering process, which is important for the systems, for the supercomputer systems, because they want to be sure that who is running something on their systems. Okay, because you can, as a student, you can ask for an allocation and then run your Bitcoin simulation on that. This is not what the system is supposed to be doing. So they want to know what to do, who is using the system. However, there are community, and the Human Brain Project is one of these, in which CSCS, for example, but also Cineca, has agreed to set up a service account which is tied to one personal account, in this case, mine personal account. And they say, okay, you are responsible for whoever run programs through this service account. We give you some amount of time. And so we set up a system in which anyone, even without having an account on a supercomputer system, can run a simulation, relatively small simulation, through the user account, to the service account in such a way that one can make the first attempt at simulations without going through the entire process of not only getting an account, but also setting up the scripts, studying the configuration of the supercomputer system, organizing the program in parallel, and so on. Once you have access to the Human Brain Project, the brain simulation platform, you will be able to use this service account automatically in a very transparent way. There are also nice things as the system monitor in such a way that if you have different accounts on different systems, you can see what is the situation before you run the simulation to avoid the problem of launching a simulation, then it never come back because the system was under maintenance or it is down for some reason, so you waste a couple of days or even more waiting for the simulation. And then there is another section which is also quite important because I'm sure you know about ModelDB. ModelDB is the reference place site where you can download and find models of any kind of neurons network that implemented at different levels. And you can download the model, again installing the model on your system, and if you're lucky, it works first time. With the live paper section of the brain simulation platform, and I think I can go on the internet now, what you can do is browse the papers which are related to some model, more or less complicated, and you have full access to not only the data, which is important, the raw data which had been used for implementing the model, but also you have access not only to the model, but you can run the model on the platform. This is one example here. So let me go to one of my papers because I know how to use it, but I'm sure that Egidio and others, Stefano, for example, here have some other examples of this. In this case, there were single cell models. You see that here you can look at the morphology that we used for the simulations. In this case, were about 50 CO1 pyramidal cell neurons. Now this is on the internet. Don't blame the platform. It is running on the platform, and you can look at the morphology and see, okay, I like it, I don't like it. There are too many bubbles here. I don't know what they are. It looks strange. I mean, you can do several different things with any morphology that had been used in the paper. However, you can also look at the traces and say, okay, let me see the traces that you have been used for these simulations. This is the current. And this is this particular trace, but there are a bunch of them. In this particular case, what we did is to collect experimental data of somatic current injection on several neurons of C1 interneurons in the hippocampus, and made a model for each of the cell types. And also you can run simulations. The way in which you run simulation here is following the paper, which means in this case, since I'm running a simulation rather than showing data, I need to access the platform. Oh. Che c'è? Ok. Così va bene?
Non in blocco maiuscolo, in blocco. No, ha messo i numeri.
Sì.
Non li ha presi.
Ok.
No, non li ha presi.
Okay, this is not my keyboard, so I need to. Okay. Underscore. Posso fare underscore? Number?
No. Adesso.
It's not going to work. No, let's go do it again. Numeri?
Sì.
Li ha presi?
Sì.
Okay, good. So it is taking the model that for that particular trace, and it is running the simulation, and you can now change the current injection, and you can add recording sites. This is running Neuron on the platform. You don't have to download Neuron on your PC. You don't have to download the model on your PC and everything else. It is done directly here. This is the Neuron, the model that we implemented in this case. You can also look at I think the dendrograms. Yes. Just to see its 3D organization and set up the simulation. You can recordings and put many recordings. You can just run the simulation, I guess. Let me see what happens. It should be the standard. I don't remember. I don't remember which one I set up. Start simulation error. So this is what happens usually during meetings in which I'm going to show something online. You can keep trying. Eventually, you get the simulation. Let me see again. That's okay. There must be some. Okay. Let me close this. Oh, it is the entire computer they're frozen now. So this is not the platform for. Well, I am relieved. Oh no, this is okay. Let me see. Let me do it again with this. In addition to this, while it is running, I'm add some. Okay. In addition to this, to the live papers, of course you can run this kind of. Okay, T-stop 300. No, the internet is not responding. No, there is something going on. Okay, never mind. Since I was expecting this, I have a movie showing you. Yes, let's close everything. Let's go to the platform again, to the presentation. In addition to this very simple simulation, you can run a very large system, in this case the hippocampus, but there is also a use case for the cerebellum. In the hippocampus, let me just run the movie. You can, thanks this has been done by John Denny, the Kurkol group at the BBP, and the model in this case is yes, it is I think it is the hippocampus. They pick up a column on it, or yes, and so you can see that this is a web interface, because the large-scale detailed models are not something for be changed or modified by the users. We set up a model which is very highly validated against experimental data, so we freeze the setup, and then you can run different simulations by doing some relatively general manipulation of the synaptic weights, of the connections, or the part of the model that you want to run, and so on. You can launch the simulation, get the results, and do some different analysis on the results of the model, such as raster plot, local field potentials, or whatever you want. We are going to improve the availability of these use cases, adding more analysis, and this is will be done especially in connection with the users, because it is up to the users to suggest new ways in which we can analyze, or adding their code. We can add the code that's developed by a user to the system, to the use case, so everybody else can run the same analysis using this specific code. Okay, so let's go. This is the analysis. It is. This is just a screenshot during an interactive session. These are the locations of the. This is calculating the local field potential. These are the location of the electrode. This is a raster plot, trace plot, and now it's going to do the local field potential and the power spectrum and so on. Okay, so let's get out of this. Some statistics, last slide. So far, the brain simulation platform has been accessed throughout the world, except Greenland, some part of Africa, and maybe some part in South America, which are never shown. We don't have students there, but we hope to have students everywhere, from everywhere. So far, there are over 600 users external to the Human Brain Project, and 150 for the Human Brain Project, and about a few thousand use cases cloned, which means that a use case clone, a user clone a use case, and from now on he can work on his own private space. Okay, and so far we have over almost 4,000 use case cloned, and this is a statistic showing that, of course, as we can imagine, the MOOC have been responsible for most use of the platform, because there are thousands of students there, and they actively use the platform as it is. I think that the last thing I want to say is that there are going to be a couple of events, probably. Almost surely a workshop on the use of Docker containers on HPC systems. This will be run mainly by CSCS people in March in Palermo. We have not defined the date yet. And we are also trying to organize a tutorial at the next Organization for Computational Neuroscience meeting in Melbourne in July. These training events are very important, and the European Union has stressed that we must do as many as possible to do dissemination activities and introduce in practical ways the more users to the platform. So I think that this concludes my presentation, and I thank you for your attention. If there are any questions, I can.
Thank you, Michele. Questions? The experience tells us that many questions come during the coffee break. So if there are no questions now, we have time to talk about the brain simulation platform and eBrains and the coffee break. Now we move upstairs. Thank you, Michele. Okay, so following the talk of Michele on eBrains and brain simulation platform and services, now we move to the first session of today on high-performance computing, and Cristiano Padavini will present this part of the project from the point of view of Cineca. Cineca is the supercomputing center of Italy in Bologna.
Thank you. So we use up to 40 virtual CPUs per node, and a memory size up to 125 gigabytes per node. And over this infrastructure, we can create your virtual machine. The access to your virtual machine is allowed via OpenStack version Liberty, and you can ask for resources contacting directly Cineca support. For the HPC resource, we have Marconi A2 that will be of production tomorrow, unfortunately. It is today a partition of our tier 0 system. Marconi is computed by 5 partitions that are accessible. 3 of that A1, this is now the Galileo system. A2, that is the Canal system, and A3, that is the SK Lake system. The A2 was a system that can achieve up to 11 petaflops. Do you know what means petaflop? Yes, okay, wonderful. And this system was a particular architecture. The node is made by 68 cores with an hyperthreading enable for 272 virtual cores per node. And the network was an Intel OmniPath at 100 gigabit per second. Then it was useful, really useful, for several applications in neuroscience during his life. Unfortunately, today is the last day of his life, and it will be substituted by Marconi 100. We expect this machine at the end of March 2020. The model will be an IBM Power 9, and if you see, we will provide 2 sockets per node, 16 cores per socket, that means 32 cores per node, up to 560 gigabytes per node RAM, and the peak performance about 32 petaflops. So we quite triplicate our power. On Marconi 100, Marconi 100, we will be defining the PRACE projects, human brain projects, and so on. And probably this will be our next tier 0 system. And now Galileo is our tier 1 system. Is made by the first partition of Marconi. This Broadwell processor, 2 socket with 18 cores per socket, and there are 16 nodes equipped with NVIDIA K80 and 2 nodes equipped with NVIDIA V100 GPU. Unfortunately, Galileo is now overbooked because we are decommissioning Marconi 2. So for next 2 months, probably will be able to host several projects. And this is not all the resources of Cineca, but is the resources that have been provided by Cineca for the human brain up to now. The data archival is connected between these three systems, the cloud, Marconi, and Galileo. And as you see, you can say there that there is a scratch or a work area that are the shared and the project data area. And then there is a home area, and those areas are our active data repository in the context of each area. And then there is a DRS or ARC or repo or tape that are data storage. This is our archival repository. And how we can use this area? Well, the home area is an area, it's a private area. It's connected to one single user. It's backuped. So normally can have a size up to 5 gigabyte, but it can be upgraded up to 50 gigabyte on motivated request. The area the work area is the right place where you can want to store your data that have to be shared between collaborators of your projects. This is private to the project. The default is 1 terabyte size, but it can be increased of several terabyte with under several agreements, not necessarily under payment. And the Cineca Scratch is the shared area, is visible to all users that are defined into the systems. Home, work, and Cineca Scratch are defined into a parallel file system, GPFS. And this GPFS is connected between data storage, archival data storage, active data storage of all systems. So you are able to see your work area defined in several systems, or you can have a duplicate of your work area in several systems. Everything is possible. Anyway, our archival data repository, that is the RES, they can be defined as a repo, as a repository or archive or tape, are visible on all systems independently, and they have a direct link to all HPC systems. You can upload from this area into your Cineca Scratch or your work area your data saved for future solution. And then you can re-upload your results into this area if you want to save this data and don't use for maybe 1, 2, 3 months, 1 year, and so on. Then there is the DRS file system, that is data that will be shared among different platforms. That means it's not only visible to the single site, but they are visible to other hosting sites. What's next? In the future, Cineca will provide into the ICI an infrastructure dedicated to the project, to Phoenix. In particular, we want to provide up to 350 nodes, 5,000 terabyte for the archival data repository, and 350 terabyte for the active data repositories. Other resources that are out of the project will be provided by Cineca via Iskra project, PRAISE project, or under agreements. The Iskra projects are national projects, Italian national project. The PRAISE project is a European massive, very high-performing simulation project. So normally the idea is that an Italian researcher have to ask for an Iskra project, and start his or her studies and his or her simulation in order to achieve the right data set that will be simulated into a project using up to, from to 1,000 nodes, so several hundred of thousand cores for your simulation, up to 2,000 or 4,000 nodes of NHP systems. It's not really easy. And finally, I want to introduce the next benchmark that will be run in Cineca in order to understand how our infrastructure should be developed for the HA project. The reference are the next, there is the next 2.14.0 based on Hippen et al. And modifies as follows. We're using a neuron model IF and PSC and alpha neuron model. A connection E2E uses the standard P underscore PL underscore synapses home HPC when plastic is set to true, while other connection use a static synapse. The network size scale is 11,250 dot your scale. And the connectivity is a 10% for scale if this is minus than 10. Otherwise, we set the CE and the CI respectively 9,000 and 2025 and 250. The user argument that I set is a scale that is 10 per the number of nodes used. Sorry. And this means that if I use much more nodes, the scale is improved. And the number of virtual processes is set as the product of number of nodes requested, the number of the tasks per node that are something like the MPI process per node that you are requesting, and the number of CPU needed per single process, per task. That means if you are using an hybrid programming. Oh my God. So you can read this as how many nodes I want, production for the number of process per node is the number of MPI process, for example, and CPU per task is your number of OpenMP threads. Do you have any experience about parallel programming? Yes. Okay. Well, then we set a simulation time and a number or a recording per neuron to 1,000. We activate the plasticity and set the mean and max to 1.5. And the results are, the benchmark I have made by 7 phases. There is a setup, neuron node creation, network connection setup, initial simulation as the single timestamp, a pre-simulation that cover the first 100 milliseconds, that is a fixed value, then the simulation, and then the finalization. And the results of our benchmark, in the case of one node with one process and 48 threads, is very similar to a run with the 2 processes and 24 threads per node. This benchmark is run on a SQL system. It's not available for human brain, but is quite similar as performance to the new machine. So this was the reason. And as you can see, this falls speed up because we take as a reference the run up on one single node is very interesting up to 16 node run. So Nestis can run in a smart way in our HPC system using up to 16 nodes. There is not really a big difference if you are using one MPI process or two MPI process per node. And there you can find your reference. I will leave this presentation to Professor D'Angelo in order to allow people to get access to much more information. Thank you very much. And sorry for the long talk.
Again, if there are no questions now, we can postpone the questions and ask later.
Thank you.
And we move to the next presentation, Emanuele. On cerebellar GPU models. So this is a technical section presenting the HPC infrastructures available for these models and the development of different strategies and different modeling approaches. For example, those based on CPUs, we've seen quite a lot yesterday, and GPUs. We'll see today two presentations, one now and one next.
Good morning, I am Emanuele Torti. I work at the Custom Computing and Programmable System Laboratory of the University of Pavia, and today my talk is about the Granular Layer Simulator, or GESS, which is a system that targets a single and multi-GPU system for reconstructing and simulating the cerebellar network. Nowadays, high-performance computing systems are capable of elaborating a huge amount of data in a reduced time. And this system has, of course, a great importance for neuroscience, in particular when we consider computational modeling. Among the different kind of HPC technologies, we exploited graphic processing unit because they are the devices that are suitable for long-lasting simulation of large-scale networks. Moreover, this device can be hosted both on a desktop system and on a supercomputer. The GESS system is made up of three main modules. The first one is the network design, then we have the network simulation, and finally the graphical user interface. Concerning the first module, it is the module that reconstructs in detail the cerebellar granular layer, placing the neurons in a 3D space. The tasks that are performed by this module are the computation of the number of elements to include inside the 3D space. Then this module places the element inside the space and then connects them following morphological rules such as convergence and divergence ratio. Moreover, it generates the connection matrices that are used in the next module, and another important thing is the clustering of the glomerulus in order to provide the input from the MOSI fiber. Concerning the network simulation, this module is in charge of reproducing the neuronal activity of granules and Golgi cells which are stimulated by the MOSI and managing the signal exchanging between the different neurons. Finally, we have the graphical user interface, which has two main tasks. The first one is to allow to non-expert user to interact with the simulator. We can, for example, change parameters or describe how to give the input from the MOSI fiber. And the other task is to visualize the network and also the results of the simulation. We have validated our system considering a network of size 600 micrometer by 150 micrometer by 1,200 micrometer. This is just our choice, but the code that we develop is fully parametric. So it means that the user can change the network size by simply interacting with the user interface. We have in this considered volume an amount of element which is shown in the slide, that in particular we have more than 500,000 elements, considering both Golgi cell, granular cell, glomeruli, and MOSI fibers. Now I will show you a short movie about the graphical user interface. The first task of this module is to show to the user how the elements are placed in the 3D space. In particular, we have, in this simplified case, neurons that are represented by spheres. We have in blue the Golgi cells, in red the granule cells, and in green the glomerulus. It is possible to interact with the network, such as changing the point of view by simply clicking with the mouse in the space, and we can also see the results of the simulation. We can see that some cells now are highlighted when they produce, for example, a spike after they receive a stimulus or for their spontaneous firing. This is just an example of an interaction. Another thing that can be done by the graphical user interface is to visualize some particular behavior of the network, such as the center surround. In this case, we have chosen to change the color of the cells from light blue to dark blue to then purple for the Golgi, and from yellow to orange and then to red for the granule. And we can see that in this place, in this area of the network, the center surround is shown, and we can also then interact with the network. Another important task of the graphical user interface is to visualize how the glomeruli are clustered into rosettes. We have developed a custom algorithm in order to follow some rules that we found in the literature. In particular, the custom algorithm is capable of clustering glomeruli in groups of 4 to 12 elements according to the results, to the data present in the literature. Concerning the computational complexity, we have chosen to show you the results that we have obtained on a desktop computer which is installed in our laboratory. And the network construction module, which means that we have to compute the number of elements, place them, connect them, and perform the clustering, runs in less than 4 minutes on an Intel i9 cluster. This is because the JAS simulator is at a higher level of optimization because we exploit low-level languages. After the generation of the connection matrix, there is the second module, which receives this matrix as input and performs the simulation. The flow of the simulator is shown in this slide. Of course, we have both serial task and parallel task. The serial tasks are, for example, data initialization and connection matrix evaluation, while the parts that are performed in parallel are highlighted in the yellow box. And in particular, we have the evaluation of the Golgi cell activity, which means that we evaluate the synaptic activity, the soma activity, and then we update the membrane potential. We have also a part that updates the gap junction current, and we have a similar module for the granule cell activity, which is very similar to the Golgi one, of course, changing parameters and so on. The key idea which is behind the use of GPU is that the GPU are devices equipped with thousands of cores, and it is possible to assign to each core of the GPU a single cell to evaluate. In this slide, we have the cells represented by the colored square at the top of the slide, and it is possible to see how, in this animation, they are assigned to a single core of the GPU. It means that we can simulate in parallel thousands of cells. Of course, we have also extended our system for exploiting multi-GPU system. In this slide, we have a flow that describes how it is possible to split the computation between, in this case, two devices, but our code is completely general and we can split among more GPUs we have, but we are also targeting a normal desktop system, so we have 2 GPUs in our lab, and the flow is similar to the previous one, with the difference that the number of cells that each GPU has to evaluate is half with respect to the previous case. Now let's see some results, preliminary results of the simulation. We have developed several testing protocols. In particular, we are considering both background activity and bursts on MOSI fibers. We have activated the full network, so all the elements that are reported in this slide, and we have performed a simulation of different times. In particular, I want to highlight the attention on the 10-second simulation. It means that we have simulated 10 seconds of neuron activity of cells that are described by an extended Hodgkin and Huxley models. If we consider a serial simulation, it takes more than 5 days. But if we consider single GPU and multi-GPU system, we can see that the times are reduced in less than 4 hours and less than 3 hours, respectively. This means that with a single desktop system, we have speed-ups that are about 38 for a single GPU system, and they are about 55 for multi-GPU system. I want to highlight that I'm always talking about desktop system. It means systems that are hosted in our laboratory on a desk. They are not supercomputer, but of course the code that we developed can run also on supercomputer or cluster systems. Concluding this simulation, we have developed the JESS simulator, which is capable of reconstructing the granular network, and it can generate a realistic network in less than 4 minutes on an Intel 9 desktop CPU. The simulator is capable of performing 10 seconds of simulation of neuronal activity in less than 4 hours, considering a single GPU system, and in less than 3 hours, considering a multi-GPU code. And we have also developed a graphical user interface that allows non-expert users to interact with the system, but also to visualize the results. In conclusion, you can see in this slide the main contributor of the JESS system, together with the contact information. So please feel free to contact us if you need more details, or if you are interested in our simulation. Thank you. If you have got questions.
Thank you for the presentation, Emanuele. There are questions, please.
Yes. Serial CPU, because serial GPU, it is not so clever solution, because a GPU are a device developed working in parallel. So we choose to run the serial code on a CPU which is optimized for run serial code. So we have the comparison between an optimized serial code which runs on the best device possible between a parallel code which runs on GPUs which are optimized for this kind of tasks. Yes, parts of the code have been parallelized with the OpenMP directive, but for the reconstruction stage, we don't need to parallelize, because we have developed highly optimize the routine. While for the multi-core CPU, we have a speed up of at least 4 or 5 with compared to between a serial CPU and a multi-core CPU, so it is not so a great speed up. We are now working for integrating different models. Now we have used the extended Hodgkin-Huxley model because they are the more realistic and more complex model. Of course, we wanted to insert different kind of models in order to allow the user to choose different kind of models, and we think that if we include leak integrated environment, we can also perform a real-time simulation considering our GPU and multi-GPU strategies.
How do you handle gap junctions when you distribute the work over multiple GPUs?
Yes, we have got the gap junction.
But is there any special technique to do that? Because it requires tight coupling.
Yes, I don't know if it is clear in the slide, but the gap junction in the multi-GPU version are performed now on a single GPU with a peer data transfer. But we are working in splitting the gap junction elaboration between 2 or more devices. I have to say that now this transfer has no weight on the simulation. I mean, it is just neglectable with respect to the performance.
Okay, thank you. If there are no more questions, the next speaker, please. Hiroshi Yamura from Numerical Brain Tokyo will present another development of cerebellar models and the human-scale cerebellum on K-computer.
Okay, thank you for the opportunity to give a presentation. I'd like to talk about building the cerebellum on a supercomputer. The brain is a complex neural network consisting of a large number of neurons. Neurons exchange information encoded by electrical pulse called spikes. Neuron receives spikes from other neuron connected by a synapse and accumulated and emitted spike to other neurons. Brain functioning such as motor control, learning, and memory and cognitive process are associated with the neural network dynamics. Left figure shows the brain mass and total number of neurons for the various species. The brain mass increased from rodent to primate to humans. In addition, the number of neurons is scaling up from rodent to primate to human. For example, rat brain has 0.2 billion neurons. Monkey brain has 6 billion neurons. And the human brain has as many as 86 billion neurons. Now let's look at the cerebellum and cerebellum. In the human brain, the 92% of brain and 99% of neuron are included in the cerebellum and cerebellum. The cerebellum occupies 82% of the brain mass, while the cerebellum occupies only 10% of the brain mass. On the other hand, the cerebellum contains 80% of all neurons, while the cerebellum contains only 90% of all neurons. So the human cerebellum comprises 69 billion neurons, most of which are granule cells. Computer simulation of the full human brain is an ambitious challenge in the field of computational neuroscience and high-performance computing. Owing to the Moore's law on the performance of the supercomputers, it is becoming possible to simulate a spiking neural network of human brain on a supercomputer. Several attempts had been made to simulate a spiking network model on supercomputers. On the cerebellum, previously, Yamazaki et al. Have built a cerebellum model consisting of 1 billion spiking neurons on Japanese supercomputer Shobu. The cerebellum model is comparable to the full cerebellum of a cat. Furthermore, they have achieved real-time simulation. Currently, in a national project called Post-K Exploratory Challenge 4, we have been building a large-scale spiking network model of the cerebellum, cerebral cortex, and basal ganglia on a K computer towards the human-scale full brain simulation. The K computer is the Japanese flagship supercomputer. The K computer is composed of 82,944 compute nodes. The total theoretical computational performance is 11 petaflops. In the Post-K Exploratory Challenge 4, we employed an in-house software dedicated to the K computer and its successor, Fugak, for computer simulation, rather than writing a simulation code from scratch. MONE is an abbreviation for Millfield-like organization neural network. The MONE simulator partitions two-dimensional sheets of a network structure into a number of square tiles and assign the tiles to compute node, and then performs calculation in parallel for the tiles. As shown in right figures, the cerebellum is known as its regular and repeated crystallized or anatomical structure. Therefore, the cerebellum is the most approximate brain region for the tile-based decomposition. So let's build the cerebellum. We built the spiking network model of the cerebellum based on experimental data of electrophysiology and anatomy using the MONE simulator. Each cerebral neuron was modeled as conductance-based link integrated fire unit. Parameter was set based on our previous studies. Top figure shows three-dimensional structure of the cerebral model for one tile. To describe anatomical structure in the brain, basic connection is defined by two-dimensional Gaussian function or an orthogonal cross function. We set the projection area and connection probability. In the MONE simulator, users can set a parameter file in a JSON format that defines the simulation setting and neural network parameter. As a benchmark, we performed computer simulation of a cerebellum-dependent eye movement task known as optokinetic response, OKR. Top left figure shows schematic of cerebellar neural circuit for OKR. In the OKR, the cerebral cortex received two input signals. Visual motion information is transmitted from the retina to the granule cell through most fibers by NRTP. Retinal sleep information is transmitted to Purkinje cell through climbing fibers by the inferior oblique. The activity of vestibular nucleus cells corresponds to eye movement. In the simulation, we fed sinusoidally modulated external current into NRTP cells. Top right figure shows raster plot of the granule cells in response to input signal in NRTP cells. Down left and down right figure shows firing rate of the Purkinje cell and vestibular nucleus cells, respectively. Purkinje cell modulated the firing rate out of phase of the firing rate of the NRTP cells. Further, vestibular nucleus cells modulated the firing rate out of phase with the firing rate of Purkinje cell due to this inhibition. The cerebral model with the Monet simulator reproduced the OKR simulation as shown by previous cerebral model. Next, to examine the scalability of the Monet simulator, we varied the number of computed nodes from 1024 to 82,944. While increasing the network size of the cerebral model and measured the computational time. In other words, we analyzed the weak scaling property of a cerebral model. We observed a good weak scaling property for our cerebral model. Using full node of the K computer, we succeeded in simulating the human scale cerebellum, although the simulation was 578 times slower than wall clock time. The cerebellum is interconnected with the cerebral cortex and basal ganglia. To understand the computational mechanism of the human cerebellum, it is necessary to consider interaction with other part of the forebrain. The Monet simulator allows us to develop different models, cerebral cortex, thalamus, and basal ganglia independently, and connect them. Although the K computer has already been shut down, we hope that next generation supercomputer such as FUGAC, will realize human-scale forebrain simulation. That's all. Thank you very much.
So thank you for this very interesting presentation. It's impressive what you are doing. Are there any questions? Claudia. Wait.
Sorry. You have different cell types within the cerebellum, but are they differentiated based just on the connection, or they have different dynamic properties, the cell types?
Yes. For example, cerebellum has main five type neuron. Each neuron has different parameters.
Okay.
And each cell has a different connection probability.
Okay. And then, sorry, the last thing, when you say that basically you exploit the whole K computer to do the full-scale cerebellum, right? So you need to scale up to connect to other structures. Okay, so these are all the nodes to simulate the whole number of neurons within the human cerebellum, right?
Yes,
Okay,
that's right.
and then, okay,
yes.
okay. Full node, sorry, I did that. Okay, thank you.
Yes, hi, yes.
Can I have another question? Now you have the full cerebellum represented in a spiking format, because this is spiking. Then you connect this cerebellum to the rest of the brain, for example, the cerebral cortex, the basal ganglia, through the thalamus. Everything is spiking.
Yes.
Yeah, and how do you implement a test or a task like, I don't know what kind of task you want to represent or simulate? Everything is spiking. So where are the commands coming from? How are the properties of a task encoded into this brain? Because normally what is more common to do is to have some analog parts in controllers, and these analog parts generate the target functions or the desired targets, or let's say the intentions of the simulator. There is a function that is written explicitly. How this explicit function is represented implicitly in a fully spiking simulator. I understand everything is spiking. I don't understand how you manage to use it. Maybe my question is not clear enough. So if you want to have your computer performing a task, for example, deciding that it has to move an arm, or it has to control a vestibulo-ocular reflex, or it has to generate a perception, how do you do it with a full spiking system? So there is nothing explicit, it's all implicit into the spike codes. No, it's not a, I think it's a fundamental question. Because I mean, I can't imagine how to do it. Maybe you know how to do it. Suppose, I mean, just to make an example to help understanding this, suppose you want to use your system to move an arm, to simulate the movement of an arm. What we normally do to simulate the movement of an arm is to give the system some cues. For example, the kinematics. We say the arm has to go from point 1 to point 2. And this is written explicitly. And then we force the system to work with these kinematics, begin the movement, send feedback signals, generate errors, and then all of this is put into the cerebellum that can be spiking, can be spinnaker, can be GPU, can be Pines, whatever we want, spiking. This cerebellum takes all these things, transforms into spikes, and the spikes are used to compute. The output of this cerebellar computation is sent out back to the motor control system, to the centers required for regulating the movement, for controlling the movement. But at the beginning, you have a priming of your system written as an equation. So the willingness of the system is written as an equation. It's not generated by spikes. I wouldn't be able to control spikes to generate the willingness of the system. So how do you work about this problem? It's not about what you construct, it's how to use it.
I think
I'm curious because, I mean, it's a fundamental issue. We will have to face it sooner or later. You or us or whoever will be able to use a fully spiking system. We have to be able to control this issue. No, I mean, I don't want to put you in troubles. I mean, but the issue is there. The issue is there. So maybe we have time to discuss it later. Yeah. So thank you very much. It was very nice, very interesting.
Thank you very much.
Okay, now we move to the last presentation of this section. Petrut.
Just Peter.
Spinnaker.
Right, so hi everyone. I'm going to try to keep this on time, because maybe we finish all the presentations before lunch. So I'm gonna try and tell you about our current journey in trying to model the cerebellum on Spinnaker. I'm gonna present a short overview of Spinnaker and what it is, lessons we've learned from trying to model, or successfully modeling a microcircuit model on Spinnaker, and then moving on to the cerebellum model that we're currently trying to run. So Spinnaker is a project started in about 2005 with the express goal of putting 1 million ARM mobile phone processors in a very large computer. It was designed to be able to model about 1% of a human brain, or about 10 mice. The result of that project was a chip, also not confusingly called Spinnaker, that contains 18 ARM cores that you can sort of see with the bluish arrow. That there's 18 processors with attached memory to each of them, and the most important bit probably is the router that I'm going to quickly cover here. So chips can communicate with each other. The whole platform is optimized for spiking neural networks. So we consider all spikes generated by neurons as being stereotypical. So the only thing we need to send to other cores or other neurons is where the spike came from, or address event representation. And because each chip is connected with 6 of its neighbors, we can send packets along through routers on each of the chips in hops. And we pride ourselves in having a multicast router technology, so a spike can be replicated on all links, all of the 6 links plus into the chip at once if needed. So a spike could go from chip 1.4 to chip 4.2, something like that, which is basically a point-to-point. You know where you're going, it's only one direction. But you can also have spikes that go to 3 chips, for example, or neurons on 3 different chips, to be more precise. And they can get replicated and sent very efficiently like this. This is the main, I guess, IP of Spinnaker. So what do we have? We have these Spinnaker chips. These are examples of 3D assemblies of chips. So you can see in the image that there's the chip that I showed earlier, plus a wire-bound SD-RAM, so large capacity but slower shared memory on top of the chip. We assemble these into boards of 48 of these beauties. And then you can assemble them into a 1 million core machine that we have as of November last year, but the platform has been operational through the HBP Collaboratory since the 30th of March in 2016, when only half of the machine was built. I'm going to not go into a lot more detail on Spinnaker, but I am going to have a shameless plug moment, because it's not every day you get your first book out. So this is going to be the Spinnaker book out in a couple of months, where you can read all about the thought process behind the design of the chip, how you create the chips, the machines, how you write software for something like this. and what kind of applications you can run on it and all of that. It's going to be an open access book, but you can also buy it. So please buy it. Okay, on to the science. Sort of recently there was a joint collaboration with Jülich Supercomputing Center to compare Markens, Diesmann's and Podjan's and Diesmann cortical microcircuit model running on Nest and running on Spinnaker. And the 77,000 neurons and almost 300 million synapses, and we could show that on Spinnaker you get very similar results to Nest. And this paper was published in Frontiers, although there was some interesting moment in time where some of our collaborators within HBP decided to do this model on GPUs, and they could show that it was faster. So Nest could do a 3 times slowdown. We could do a 20 times slowdown because Spinnaker was not designed for, it wasn't originally designed for that kind of network. When my supervisor and the rest of the group were designing the chip, they were going off of, we're going to have 1,000 neurons per core with 1,000 synapses each, receiving firing of about 10 hertz, which is not realistic, we now know. But after a year and some redesign and rethink of the software, we were able to do it in real time at while also reducing the energy efficiency of the computation by an order of magnitude, so actually beating Nest, and the GPU, but not in energy efficiency though, at the cost of simply using more cores. But as I noted earlier, we have 1 million of these, so it's not a huge problem. It was barely felt for the big machine. This was about a 12-board job, and we have 600 of them. Now the challenge is to do the same thing, but for the scaffold model that was presented yesterday and probably will be presented again today in the tutorials. This model comes with very interesting features, but also challenges for us. It also has about 96,000 cells, all leaky, integrate, and fire, and about 4.2 million synapses, although they're organized differently than in the cortical microcircuit. I mean, you've heard these before, but it's a data-driven design of the network with connectivity generated based on experimental observation and constraints, with activity that matches experiments seen from PyNest and PyNeuron, both qualitatively and quantitatively, which is a problem for us. It would seem that Spinnaker doesn't really like biology as much, but I'm sure we can make it work. Some of the features that we need to design for, as far as we're aware currently, is we need to account for the maximum number of spikes in a time step if we want to have this particular cerebellum model running in real time on Spinnaker, which would mean individual Purkinje cells, for example, being able, or individual cores simulating the Purkinje cells, I should say, being able to deal with about 17,000 spikes in one time step. And I'm going to get to a few slides down to explain exactly how many spikes we could do for the cortical microcircuit that allowed us to do it in real time. We also have slight numerical constraints, as Spinnaker does not have floating point units, and they're 32-bit ARM processors from 2005. So they're not particularly powerful. So currently the results that I'm showing on screen but not explaining are generated by slowing down the machine by about 2,000 times slower than real time. And they're not 100% correct. There's still more to do to both speed this up and increase the, let's say, the accuracy or the fidelity of the simulation. So what the lessons that we're trying to take from the cortical microcircuit are doing the software differently, or making it much more specialized for the task at hand. So what are we currently doing with Spinnaker? Well, Spinnaker, again, has 18 ARM cores per each chip. Currently, if you go and run experiments, even right now, through the collaboratory, or I also have a board, physical board with me if the internet is bad here, and if you want to try something, you will get, on each processing core that is being used, you will get both software that updates the neuron state and updates the synapse state. If you want any Poisson input or anything like that, they would be, those kinds of inputs will be communicated via spikes. And even more, if you sometimes want delays that are not currently, so synaptic delays that are not currently supported by the tools, whatever that means, you will also get these kinds of delay cores that just act as buffers and resend spikes when needed. Well, this is the traditional mapping and how we've done things. And this is how the cerebellum model has been run currently, and how the microcircuit, the cortical microcircuit, has been run originally for the inefficient runs. Yeah. What we've learned from this is that we could do things differently by having dedicated cores that do either neuron updates or synapse processing, but not both. And in this scenario, synapse cores that only compute the synaptic inputs can communicate the current needed to the neuron through shared memory. So we're alleviating the problem of overloading the communication fabric. And this is exactly what allows us, well, this is one of the many reasons that allows us to run the cortical microcircuit in real time. What I wanted to say about this is that you see these synapse cores here. There are about 3 of them. It says SL, SU, and S, but I don't know how far from the back you can see this. They're basically split into 2 synapse cores per excitatory connections, and for the excitatory connections, and the red synapse core for the inhibitory connections. We can split this more finely. However, we've noticed that in order to maintain a real-time performance using this kind of architecture, each synapse core is able, in the time given, to process 20 spikes. 20 spikes for real-time performance for core. Which is not something we can do for 17,000 incoming spikes per one cell currently, which is the challenge that we need to face here, being able to use up to 800 cores just for synapse processing for a neuron if we're aiming for real time in the worst case scenarios. So this could be done. This is a potential solution. We're still investigating exactly if this is possible and how this can be done, but you could have your neuron somewhere on a chip, and then all the other chips around that one that's doing neuron state updates, all of them just doing synapses and communicating their updates once in a while at the end of a time step. Again, this hasn't been attempted ever on Spinnaker, but if this is successful, then it would mean that any model with any sort of fan-in should be possible, allowing us to do all of the things that we promised with the Spinnaker platform. Some of them being, you could have robot control systems using biophysically constrained models rather than simplified models of this, say, cerebellum. You can simulate the cerebellum like we have for the cortical microcircuit over days or weeks, at the cost of days or weeks, right? Because this would be real time. But it would also allow you to run online learning experiments that necessitate real-time interaction, say for robotics. If a robot is trying to learn something, you'd like it to do it now rather than in 2 days or 2 weeks. And also because we have full control over the platform, you could also induce pathologies and then study their behavior in, say, a robot or in a simulated environment like the NRP, the neurorobotics platform of the HBP. So in summary, we have been able to run cortical simulations on Spinnaker in real time and with some tweaking of the software with an order of magnitude energy reduction per operation. Now for the cerebellum, it's a difficult problem that we're still analyzing. The key might be to scale off chip, so recruit nearby chips to do just synapse processing and nothing else. But this could open, if this is successful, this could open a huge avenue of further exploration. Thank you, and I'm on time.
Thank you, Petrut, for the presentation. And any questions about Spinnaker? Please.
What is the ODE solver that you're using on Spinnaker?
Custom. Because of the, I'm not familiar fully with how this is done, but because we have a constraint of not using a floating point unit, a lot of it had to be very carefully designed for numerical stability. And I think it also, the ODE solver differs based on if it's a LIF, a leaky integrate and fire neuron, versus the Zikvich model that we have on Spinnaker. But I can't give you a proper response to that.
Okay.
I can point you to the paper, I just can't remember.
That will also do.
More questions? Thank you, Petrut.
Thank you.
Okay, we move now into the next section. It's the time of Werner from EPFL. Optimization, validation, and simplification. There are 3 fundamental steps for the production and use of reliable models. So now, optimization with BluePyOpt.
Okay, so I'll describe to you one of our softwares that we've developed at the Blueprint project. So Stefano Mazzoli yesterday already mentioned it, and there will also be some tutorials this afternoon about it. So it's basically a software that's used to optimize parameters of neuron models. So let me first describe the problem a bit. So you basically have a morphology of a neuron, which is fairly easy to reconstruct. I mean, it takes time, but it's not too difficult. But as Stefano also mentioned yesterday, it's virtually impossible to figure out where all the ion channels on the dendrites of these neurons are. So it's not trivial to get all the data to reconstruct the electrical activity of the neuron. And so we basically have, like if we do whole cell patch clamp recordings, we do have the electrical response of the neuron. So we inject like a step current and we look at the activity of the neuron. And now we basically need some software that, I mean, given this as constraints of your electrical activity, can put your ion channels onto the shape of the morphology and constrain basically your parameters. So, I mean, this is, for example, I mean, here it shows a bit the complexity of the problem. So you have all these, I mean, on the x-axis, you have all the different parameters. So it's basically like all the distributions of your ion channels in different regions of the neuron. And, I mean, all these parameters, they have different ranges, basically. I mean, this is actually a log scale. And you even have, I mean, even we also know from biology, like papers from Yves Marder have shown that in the 2000s, that, I mean, even a neuron, to get the same activity, so to have the same, to generate the same activity, can even have a different set of parameters that generate that same activity. And so the idea is that your algorithm searches in this space to find the good solutions. So let me first introduce one software that's basically used by BluePyOpt, and that will also be shown by this afternoon in the tutorial. So that's eFel. I mean, as you can see, our evaluation target is basically these traces here. One option would be to try to match these traces exactly, but that's not trivial, because I mean, if you just have like a little shift in time or something in between your model and your experimental data, it generates lots of errors and things like that. So one approach that was come up also again in the years 2000 was to use a feature-based approach. So you, instead of trying to match exactly, you first calculate certain features from the trace. So for example, I mean, you calculate the spike heights, spike widths. And so for this, we have this tool called eFel. So it's an open source tool. It's available on GitHub. With this, I mean, here I just show a single spike, but you can also just give it a trace of several spikes, and it will calculate also the frequency of the spikes and all kinds of things. And so this tool is used both for experimental data, so to get the constraints basically, and also it's also used on the data generated by the models to compare with the experimental data. So then, I mean, once we have our constraints, basically we run our parameter optimization. So in case of BluePyOpt, this is done using evolutionary algorithms. So I mean, just for people who are not familiar with these algorithms, so it's basically you have your algorithm, you've got your model with certain parameters, and so your evolutionary algorithm basically creates basically a set of individuals. An individual is like a set of parameters that it wants to see if these are good enough or not. So it feeds these parameters into the model. I mean, once you have a certain, once you have these models with these parameter values, you generate the traces, you create a score, so it shows how well your model matches the experimental data. And once you have this score, you basically make a selection. So you only keep the best individuals from every generation, because it's like an iterative process. And once you keep these, you create new individuals using mutation and crossover. So like your individuals, they basically mate with each other, and they create new solutions, and then you also mutate these solutions. So it's basically an iterative process in which your parameters become better and better. I mean, this is the very simplified schematic of it. I mean, the evolutionary algorithms can be very complex, but that's the main idea. So, I mean, of course, everybody can implement their own genetic algorithm, but we wanted to create a tool that would make it easy for neuroscientists to just apply this genetic algorithm to their problem. So for that, we created BluePyOpt. So it basically hides the complexity of the evolutionary algorithm itself. I mean, you can still give it some parameters of the algorithm, but it also has default values, so you don't really have to know much about the algorithm itself to use it. And again, it's a pip installable package with Python, so you can it's open source. You can download it from GitHub and run it from there. So it uses, I mean, it's a bit of a technical thing, but so it uses another library actually, so that's not written by us, it's a general library for genetic algorithms called Deep. Yeah, I mean, BluePyOpt is also pure Python, so you don't need to compile anything. It works out of the box. I mean, the only thing that you mostly need is the neuron simulator, which is maybe a bit more difficult to install, but BluePyOpt itself should not be a big issue. So let me give a little example of how things work. So, for example, I mean, here, let's say we have a single compartmental model with just two parameters. So we just have a sodium conductance and a potassium conductance. And we just want to find like certain values for these two parameters. And our constraints is that our model should fire once if we inject a certain current, and if we inject a slightly higher current, it should fire 5 times. So you basically can, I mean, actually this particular example is also described in the BluePyOpt paper, and it's also available on the GitHub as an example code. But so you basically give this problem to BluePyOpt, and then you basically get something back like this. So here you see the parameter values. So you have the conductance of the sodium conductance. Sorry, the strength of the sodium conductance and the strength of the potassium conductance, and then you can see where in the space your solution is doing very well. So all these dots here are actually solutions where the score is perfect. So it means it has exactly the right amount of spikes that we asked in as constraint. And yeah, you see that there's also like some gradients in the parameter space. I mean, of course, this is this is all based on the neuron simulator and on fitting the conductances of ion channels. But I also want to point out that it's not necessarily, you can also use it for general optimization. So, for example, also, I mean, this is a model that was fit by a plasticity model fit by somebody in our group, where we basically wanted to, where we have the data points here in red are the constraints we want to stay within, and then we basically have an analytical solution that we want to get into these constraints. And so the blue lines here are basically the parameters of an analytical equation that were basically matching perfectly with the experimental data. But I mean, this example doesn't use any neuron simulator at all. It's just a pure analytical equation you're trying to fit the parameters to. I also just want to mention some use cases of people basically that have been using BluePyOpt over the years now. So we have Egidio D'Angelo's group who has been using it for cerebellar cell models. We have Michele Migliori for hippocampal cell models. The Allen Institute is also using it for visual cortex models and also some human cell models actually. Then also Idan Seger's group are using it for human cells. KTH is using it for basal ganglia. I mean, they just mentioned that the paper was submitted yesterday. So, and in the Blue Brain project, we're using it for our thalamical cell models, our somatosensory cortex cell models, and also, like I mentioned, like synaptic plasticity models. And I mean, there are more people over the world that are also using it for other use cases. Then I also want to mention, I mean, for people that are a bit familiar with BluePyOpt, I also added a bit of newer things, basically. So, I mean, I also want to mention that this summer we hired a new person in my group, Tanguy Damar, who will basically be taking over most of the software development of BluePyOpt. And as a first task, I basically gave him to check how he can do hyperparameter tuning. So basically hyperparameter tuning is, I mean, BluePyOpt itself tunes the parameters of your model, but the thing is that your evolutionary algorithm itself actually also has parameters. So for example, it has mutation probability, crossover probability, crowding distance, offspring size. So it's like all things that you can tune from the algorithm itself. So the question is like, it's like a hyper optimization, like which of these parameters are best for our problems. So he basically applied this to our layer 5 pyramidal cell optimization that was in our paper, and he tried to find, tried to see what the best parameters were. So yeah, first of all, I just want to, because I mentioned crowding distance, so let me just go back here. So I mean, mutation probability and crossover probability, that's I think fairly obvious. So it's just like whenever you have an individual, all your parameters have a certain probability of mutating or doing crossover. So I mean, that's just a value between 0 and 1, basically. That's obvious. Then offspring size, that's just like how many children you get for all your parents. So that's also fairly trivial. But then the crowding distance may be a bit less trivial. So, so the way that we use the genetic algorithm basically uses something called simulated binary crossover. So it's basically, let's say your parents, I mean, you have two parents, so one parent has a parameter with a value of 2, another parameter has another parent has a parameter with a value of 5, and you want to find a value for the children. Then this operator basically puts this function on top of your parameters, and with a certain probability here you get the child will get with the probability you see here as a density these values, and then you have something called the crowding distance or the eta parameter, which controls how this distribution looks like. So if you have a value of 2, so a smaller value, you get a broader distribution, while if you get a higher value like 5, you get a narrower distribution. So this is also a parameter of our optimization algorithm. And so, just as some initial results, Tanguy basically ran our optimization with all kinds of, with different seeds basically our general layer 5 pyramidal cell optimization. And so he found that, for example, for mutation probabilities, at least for this specific case, it looks like we are actually using a pretty good value because, so we are, the default value that we're using for mutation probability is 1. So it's actually, it's getting better the higher you go here. Then the crossover probability, that's, I would say statistically it's not really significant. So there we have to do further checks, so maybe run more seeds, maybe it gets narrower if we run more seeds. For the crowding distance though, it looks like there is also some trend, like at least you shouldn't go too small for the crowding degree, so you shouldn't go too small. And again, this is preliminary results, but we probably should check if it might be better to use higher values there. And for offspring size, there's actually, I think it's also pretty important for the people using BluePyOpt. So it looks like if you go too crazy and small, like 50 offspring size, you actually get a worse result. But you don't get much improvement in the offspring size here. And actually offspring size is like the computational time that you spend, or the amount of computation that BluePyOpt will use. So it's best to stay around 100 or 200 offspring. It's no use to go much higher. It's just, again, this is all depending on the problem also, right? So this is for the layer 5 pyramidal cell. These are the results, but you have to be a bit careful to generalize this to all the problems. And then he also made some correlations basically between the two, where you can see. So it's also not just like a linear linear or independent thing. So also if you plot them against each other, they're also good values. So something that we might consider is like making this a bit more automated, and that you could, like, if you want to optimize something, that we develop some tool that you can do automatic hyperparameter search in your space to figure out the best parameters to use. Then I also want to mention just again some fairly small recent changes, but which might be important for the users at the moment. So first of all, we have switched to a new way of a new package for multiprocessing, which is called Pebbles. That in itself is not super important, but maybe important is that now you can specify actually a timeout value for your evaluation. So if your evaluation, let's say, takes half an hour or something on average, but sometimes some individuals take very long time to evaluate, then now you can put a timeout value and say, like, if a certain individual takes too long, just cut it and consider it as a bad solution, which could actually speed up a lot your optimization, because you get rid of all the slow solutions. Then we are also starting to implement stagnation criteria, so that you can decide when your optimization is actually stagnating, so it doesn't get any better. And then, that's also something I just wanted to mention, but that's a very thing. So we have made a tiny change based on a comment from somebody in the way that the distance to the soma is calculated. So before it was calculated from 0, 0, but now it's calculated from the center. So it means that your solutions might, your optimization, if you rerun them, they might slightly change their values. But I mean, in general, it's not a thing. And then I also want to mention, yeah, I mean, so that Python 2 is basically deprecated. So we keep on supporting it, but for now, but you should, as quickly as possible, move all your optimization code to Python 3 because we might drop Python 2 in the near future. And then for the future of BluePy itself, so we're also thinking about implementing new types of optimization algorithms. We also have, we are doing more, I mean, yeah, we're going further into this hyperparameter tuning. And for example, I mean, Elisabetta Iavaroni in our group, she also published a paper recently about thalamic cell models, and there she also shows some sensitivity analysis of the models, and it's also something that you might consider building into BluePy, or at least giving instructions how to do it. I mean, actually her example code of all of this is on the BluePy repository, so if you already want to try that, you can look at it there. And I also want to mention for our collaborators that we basically formed a new team in the BluePy project, the cells team. So yeah, I mean, we have hired some new people, so if in the future, if you collaborate with us, you might see some new faces and things like that. That's, yeah, that's for next meetings, I guess. We'll see maybe new people. So that's it. If there are any questions.
So thank you, Werner, for this presentation. There are any questions? Claudia?
I mean, stagnation criteria is somehow equivalent to stop criteria when you don't get a significant improvement of the fitness function.
Yeah, I don't know if, I mean, we just call it stagnation criteria.
Ah, okay.
Yeah, it's basically a stop criteria.
Okay.
Yeah, it checks if it's stagnating.
Okay.
And then it stops.
You don't get, okay.
So, yeah.
Stop your algorithm, I mean.
Yeah. Why you can still, you first detect if it's stagnant, and then you can still decide maybe to do something or to switch another algorithm or something. Right?
Okay, now there is another important step in the generation and use of the models, that is experimental model validation. Normally, for those making the codes and making the models, the experimental validation is not a critical element or a critical target. But it is critical indeed, because a model needs to be validated. If it is not validated, it's not a good model, or it's not usable. It's just a toy. It should not be a toy. It must be a piece of science. And again, talking about validation means going back to the need of the models, why we need the models and how we use the models. It is critical indeed. So, sorry, but the keyboard is very short and... Okay, now we're back to the slides. So, how do we have to conceive the process of generating the models? First of all, we need the data. Without the data, we do not make the models. So the models are not something that is invented. It's something that reflects nature. So the model is based on the data. And the data can be distributed at the different levels, can be molecular and subcellular data, can be at the neuronal level, macrocircuit and meso-macrocircuit level, or system level and behavior. So what we need are data at the proper level. I will speak mostly in this short presentation about data at the molecular and cellular level. Then once we have the data, we need the data to construct the model. The model, once it's constructed, it needs to be validated. And when it is validated, we can use it. First of all, we can propagate the model into larger constructs. For example, a neuronal model can be propagated into a microcircuit model. The microcircuit model can be embedded into a system that uses the model to generate some more complicated, higher level functions. And finally, all the construction can be used to generate a closed loop simulation. So this is normally the life of a model. From the data to the model to the propagation, validation, embedding, and use for simulations. Once we have the simulation, we generate an hypothesis, because what comes out from a model is not real, is simulated. And this simulation can be used to generate a hypothesis that can to be tested in real life. So the model is part of a cycle. I would say the life cycle of a model is inside the life cycle of our reasoning, which means taking the data, making the model, generating a hypothesis for a simulation, and testing what we've seen. That's the way science goes on since ever. Central role of data. The data are needed for model construction. Now we'll see how. Without data, no reliable models. The data not used for construction are needed for validation. So we do not have to go into a loop, a circular loop. We can't use the data that we have in the model to validate the model, because then we generate a tautology, then we validate ourselves. It's not correct, it's wrong. So the data not used for construction can be used for validation. Then the models validated, which means we begin to believe in it, can be used to predict something new that was not anticipated during the construction validation steps. And then this model that begins to be predictive promotes the need for getting new data that confirm or invalidate the hypothesis produced by the simulations. By saying that, we try to generate a sort of semantic of what we're talking about. So we are talking about validation of a model using data not used previously to construct a model. This generates something interesting for the cerebellum, where we have data at all the levels. The same picture that I showed yesterday is played back today. The data we'll speak about today are data taken at the molecular, subcellular, and neuronal and microcircuit level. So I stay in this area. I don't speak about the data at the higher levels. And this is again the pictures I played yesterday. And you see that this interchange between the models and the data occurs at all the levels. Sorry. Something happened, unwanted. At all the levels. For example, we have cellular data for cellular level models, and then we have microcircuit data for the microcircuit level models, and so forth. From the microcircuit to the large-scale circuit, we have a jump where it is difficult to have the data for construction, and we normally go into the predictions. So basically, this data can be used to generate microcircuits that are embedded, for example, in closed-loop simulations used for robotics or used for the virtual brains, with transformations of the model that we will see tomorrow. What is the nature of single-cell data? The nature of single-cell data, in many cases, is this one, in which we have traces showing membrane potential changes over time. These time-dependent changes in voltage are the activity of the neuron. In our models, these activities of the neurons are the templates of the optimization that was showed in the previous talks. So we need templates. This is the template. And are also the target. What is the output of a model? The output of a model is this kind of trace. This is what we appreciate better as an output of the model. There are many parameters as the output of a model, but this is the most important. So the output of the model is a voltage trace. This voltage trace is different for the different cells or for the different cell models. which means that we have different ways the neuron can generate voltage changes. What is more important for us is to understand how the spikes are generated and how the neuron encodes information through the spikes. The two examples are for the granule cell and the Golgi cell, which are two of the most important cells of the cerebellum. The theory that we use and we couple to the models, basically the models go into the theory, implement the parameters of the theory. The theory is based on the general equation of the membrane of a neuron that is implemented into morphologies using the transformation of single-point neurons into extended morphologically detailed neurons, in which we have compartments, and each compartment represents the portion of the neuron in which we have the differential equations for voltage current transformation in the membrane. The most important thing here is to represent the conductances. The conductances derive from physiology as well, and the conductances can be divided into conductances of the ionic channels in the membrane and conductances of the receptor into the synapses. For all these conductances, we have representations, mathematical representations, in terms of differential equations. The most famous one is the Hodgkin-Huxley representation of ionic channels, of ionic channel gating, I would say. And again, to go back to the previous presentations, the three parameters that we need to optimize are the maximum conductances of these ionic channels. So the template is voltage, the maximum conductances are the parameters to be optimized. The biophysics of the neuron is the biophysics of the neuron that is well described over the years and is casted in sort of general formalism that we can all use. So whoever of us is dealing with a neuron has to use the general formalism of cellular biophysics that allows to describe the generation of spikes and the generation of membrane potential changes in terms of this master equation that you see here, in which current is represented as the first derivative of voltage plus all the resistive terms describing the flow of ions through the membrane. So this is the general structure of our models. Okay. By saying that, see what happens when we apply this strategy of work to real neurons in the cerebellum. This is an example that developed over the years. Also consider the time span. The first works were done at the end of the 90s. Why the end of the 90s? Because at that time there were two things happening. Patch clamp techniques became rather, let's say, not common yet, but diffused. The cerebellum was one of the places where the patch clamp techniques have been pioneered. The first recordings were published by Sackman on culture cells. Then the first recordings and slices came in '89, the famous paper by Edwards, Francis Edwards. In '89 there was the first recording from neurons in slices. The second paper was in the cerebellum, that was our paper on the granule cells in 1990. So the cerebellum was a pioneer also in the patch clamp techniques, allowing to get the critical recordings that have been used later for the models. The models of the cerebellum, of the cerebellar neurons, started by the end of the 90s because there were so many informations coming about the properties of the membrane and the properties of the ionic channels of the neurons that were unexplained. They were totally uncorrelated. Papers on one channel, papers on the other ionic channel, papers on the voltage, papers on spikes, whatever, all uncorrelated. So we decided to begin to put this knowledge together and generate models, coherent models based on cellular biophysics. And then we started to use the simulator neuron. The first models were handmade. We did the models ourselves. I did the model myself. I wrote the models. But then clearly having a platform that was developing in parallel at Yale, it was very attractive. We started to use it. It was the first use of neuron in Europe. So that was the end of the 90s. We started with neuron. And the models began to tell us what the different neurons of the cerebellum were doing. The first description was done with the granule cells, and this is another nice example. It has been mentioned by our speakers today. It's the most numerous neuron of the brain. There are billions of these neurons in the brain of humans. And they are also famous because they are said to be the simplest neurons of the brain. You will see this is not true. They're very complicated. So there are continuously new findings on these neurons that are changing the way we understand the neurons. A special property of granule cells, to be concrete, is that it allowed at the beginning to record with high precision the electrical properties because electrotonically the neuron is very compact. It is so compact that it allowed to determine with precision the ionic currents and to generate constraints for the parametrization of the maximum conductances. At the beginning, there were no blue pi-opt and other optimization techniques, nothing of that. So the parametrization was a sort of art. And to get out of, I would say, the personal feeling about the values to be given to the conductances, we needed parameter range. And these were available for the granule cell, but not for the other neurons of the brain. That's why we started with the granule cells. So the first models were well constrained because we knew the parameter range. So what happened there is that we knew the parameter range, we knew quite a lot about the pharmacology of membrane ionic channels, and what we did was to construct the first model. The first model contained 7 ionic channels. We ran the model, and since we believed it was predictive, we discovered the model didn't predict all the states of the neuron. It predicted all except one, which was low threshold oscillations and resonance. These were not predicted, so something was missing. And this is what happened at the end of the 90s. And the first model predicted the existence of a new ionic channel that was not known. It was the M-like current of the granule cell that was searched, looked for, discovered, described, introduced into the model, and then all the model began to work. All the states of the model were explained, and the cell were explained. So that was the first part of the story. Then we got nice spikes and the nice properties of the neuron in a single point neuron. But the story was just the beginning, because then the size of the spike was not correct. You can say, well, it's a question of parametrization, sure, but we couldn't force the parameters because we had the range. So whatever we did, the spike was not the right shape, was too big. So the hypothesis was, well, it is too big because the ionic channels are not in the right place. We have a single point neuron. We have to make a multi-compartment neuron. And then we looked for the displacement and the location of the sodium channels. That was really the beginning of the story, because the sodium channels didn't show up in the soma, but they were only in the initial segment and in the axon. And then we moved the sodium channels into the axon. We moved them into the axon, and immediately the spike size became the real one. The reason is very simple. If you put the ionic channels in the axon, then you have a lot of current locally in the axon that generates the spikes very well. This current flows back into the soma and runs on the resistance of the soma. In this way, there is a voltage drop, Ohm's law. The voltage drop causes the spike seen from the soma to go down, but in the axon it is a very nice and full-blown spike. That was perfect. So that was the second paper. That was, I think, in 2007. There was another problem. The problem is that then we thought, if this axon is so nice in the axonal initial segment, it should travel nicely along the axon down to the parallel fibers. And we know it happens. Neurons without traveling spikes are not useful neurons. They serve to nothing. Then we did it. We constructed the parallel fibers in the model, but there was no traveling of the spikes. The spike was decremental and vanished in a few hundreds of micrometers of axon. That was wrong. Why? And then we started another work. We started to try to understand why the model was not correct in predicting the traveling of the spike in the axon. We did recordings of single spikes in the axon, of single neurons, using optical techniques, and we coupled them with electrophysiology and with some other tricks, experimental determinations. And what we found was that the properties of the sodium channels in the initial segment and in the axon are different, because there is a modulatory protein called FHF that changes the gating of the ionic channels in the axon. We did a determination of these properties. We have put the different channels in the initial segment and in the continuation of the axon. And then we also corrected the resistance of the axon that turned out to be much higher than previously thought. By putting these properties into the model, we obtained perfectly traveling spikes. This is the paper that came out 2 years ago, this year. And therefore, now we understand a bit more from these very simple cells, the simplest cells of the brain. And it is not so simple. It's continuously a source of understanding of how the neurons work. And this is because we're using the models. And the models are inspiring experiments, and the experiments go back to the models. Well, the story seemed to be solved. This was not solved, because then by analyzing the pattern of discharge of these neurons, we discovered they are much more complicated than expected. Again, statement that the granule cells are all identical one to each other. They all make regular firing. It's not true. If you analyze them carefully, they do not all make the same firing pattern. Some are regular, some accelerate, and some decelerate with time. And we started to try to understand it. The model didn't predict acceleration, but it could predict the deceleration because of some form of adaptation. How to get acceleration of firing? One channel was missing. That's another prediction. We looked into the channels that are potentially capable of generating a firing acceleration, and one of these candidate channels was the TRPM4 channel. We looked for the TRPM4. It is present in granule cells. We have recorded the currents of the TRPM4 in granule cells. We've put this channel into the model, and once we put it into the model, we transform granule cells into accelerating granule cells. Again, this is a new story that is now again submitted for publication. It's going well, I would say. And now we have another step. So instead of 8 channels, now we have 9 channels distributed across the different parts of the neuron. This means that the neuron is a very complicated machine in which you have to take into account all the properties. Now you can say, if you wanted to propagate into big network, you need all these properties into the neurons of your big network. Well, in principle, one can say, well, I put everything inside the big network. I start very let's say, from scratch, and I keep all the properties into the big networks, and I connect the big brains of big networks with a lot of properties. Well, I'm not sure it's a winning card, because then the complexity is so big that we can't control it, and also the computational power needed to solve this kind of very complex networks would be extremely large and probably impossible to sustain. Therefore, we need simplification. So how does the simplification work? And Alice will show it in the next presentation. Simplification works in a way that we can maintain these properties after we have done the simplification. So we have to understand the properties that we want to maintain in a neuron, and then in the simplified version, we have to maintain these properties. You will see this in the next step, in the next round. There was another example that was very nice, was about the Purkinje neurons, but I'm understanding time is running, so I can't do it. I just show you what happens when we jump into the network. When we jump into the network with these neurons, we can try to understand how to, what is the impact of these properties at the network level. Just to make you an example, at the network level, the granule cells are connected with the Golgi cells. The level of connectivity is complex, and it has been worked out also at the moment with Stefano and the others in the laboratory. We're working out the connectivity of granular cells and Golgi cells with experiments and with models. And what happens here is that the models constructed on the basis of the principles of granular layer connectivity that are known at the moment, and using the neurons and the neuron models that are available at the moment, makes predictions. And these predictions can be validated. For example, we can make the prediction that the arrangement of neurons into the granular layer generates center surrounds, like this, which means when you stimulate a bundle of fibers, you have a core of activity surrounded by inhibition. It's a prediction. We've done the experiments with two-photon microscopy, and we find exactly a center surround, a core of excitation surrounded by inhibition. So the model begins to be predictive in terms of properties that were not anticipated. So we were not anticipating that the model had to do that. But now the model is predicting something that is found in the experiments. Another example is that of ensemble oscillations into the network. The model predicts that under certain conditions, the network of the cerebellum can generate low-frequency oscillations in the theta and alpha range. Well, these oscillations are found experimentally. These oscillations are found in vivo, in rats, in monkeys, and maybe in humans, we don't know, because has never been done. But these oscillations are present in the cerebellum of mammals. So therefore, the model is predicting the space and time properties of the network, starting from local connectivity and neuronal properties. That's the end, so you can start with the questions, right?
Where do these oscillations enter the cerebellum? At what neuron?
Yeah, the way we obtained these oscillations in the model was to generate a random input, and this random input over the mossy fibers, which are the input fibers of the cerebellum, activates the granular cells. The activation of the granular cells is sparse. These granular cells, as an avalanche, activate the Golgi cells. The Golgi cells are much slower in getting charged by the granular cell inputs, are bigger. So they need time, so they slowly grow and grow and grow until they make a spike. The Golgi cells are all coupled one to each other through gap junctions and through inhibitory connections. So once you activate a group of Golgi cells, they tend to fire together. In a very short time, they synchronize and they fire together. And they give a feedback inhibition to all the field of granular cells that stay around them. So you have this build-up. After the build-up, the Golgi cells, bam, they stop. And then the build-up starts again. And this is the reason of the oscillation. Okay. And it's like a van der Pol oscillator, charge, discharge. You charge until you reach the threshold, and then bam, you discharge, you stop, and you start again. And this system oscillates naturally and spontaneously at a frequency between 4 and 20 Hertz, which is actually what has been found experimentally. Which means the parameters into the cells and the connections are more or less okay. Yeah.
Okay, thank you.
Clearly, in vivo, there could be another phenomenon overimposing on this, which is activity that is already oscillating coming from outside, for example, from the cortex. If the cortex oscillates, what I think is that this oscillation encounters a system that is already prone to oscillate and can be tuned in a certain range of frequencies. So it is a sort of resonator, not with a peak of resonance in a single frequency, but with a broad spectrum in which this resonance can be used. If you have an oscillation coming from the cortex between 4 and 20 Hertz, you will find a network ready to keep the oscillation and continue and get tuned on that frequency. So that's what we think. And actually, there are recordings done with magnetoencephalography in humans in which the cerebellar network is seen as a part of a coherent system of oscillators, including the cerebellar network, the prefrontal cortex, the premotor, motor, and also parietal. So this actually has something to do with real happenings. Yeah. If there are no more questions, Alice.
Okay, so good morning, everyone. I'm Alice from the Neurocomputational GDOS lab at the University of Pavia. And as the GDO already said, we will now address the issue of simplifying single neuron models to point neurons in order to be able not just to represent the single neuron activity in a single neuron simulation, but also to embed these point neurons into large-scale spiking neural network simulations and finally into closed-loop controllers to eventually simulate behaviors. As has already been said during these 2 days, neuronal communication is not just based on regular spiking patterns with a frequency that depends on an input current, but neurons, specifically also in the cerebellum, can exhibit different spiking patterns of activity. So we can have autorhythm and subthreshold oscillations with a zero input current, as you can see in the panel on the left, or with increase in depolarizing current steps, we can have linear increase of the output firing rate, but also more complex behaviors like depolarization-induced bursting and spike frequency adaptation. So a reduced adaptation after depolarizing continuously the neuron. Other properties are phase reset for neurons that exhibit autorhythm. So if an external impulse arrives, they reset the phase of their pacemaking independently of the phase of the spikes before the stimulus. Then bursts after hyperpolarization, which is going to amplify the effect of an external inhibitory input. And finally, resonance, which is an amplification of the spiking response of the neuron when the input stimulus is within a certain frequency range. These electroresponsive features, which are mainly different spiking patterns, are fundamental not just for the activity of the single neurons, but they are so important in view of simulating large-scale spiking neural networks because they impact on network dynamics, on plasticity enhancement, on noise filtering of input signals, and also, as Egidio was said before, on communication with other brain areas, because if we have a signal in a certain frequency range coming from the cortex, for example, and the input layer of the cerebellum is amplifying the signals in that frequency range, that's going to improve the communication between the different brain areas. In the cerebellum, the different cell types have been fully characterized also in previous decades in literature experiments. And it's possible to identify for each cell type a specific electroresponsive phenotype. So for all the properties we have seen before, we can identify which properties are present or not, and at which is their quantitative properties. So we have a solid basis of experimental evidence for each cerebellar neuron type. So when we are modeling cerebellar neurons and we want to move from morphologically and electrically detailed neuron models, we have to keep in mind that this complexity, which is in this case just related to the electroresponsive features more than to the morphological features, needs to be taken into account. So that the simplification is not removing the properties which are supposed to impact on network dynamics and on plasticity. Of course, we are losing something, but we are relying on the knowledge we generate in experiments and in detailed model simulations. This step is fundamental if we think that, of course, moving from detailed to simplified models, we have to address the issue of the compromise between the biological plausibility and the computational load. As you already know, these two words are mainly based on the two formalism of the Hodgkin-Huxley model, which is biologically plausible but has a higher computational load. And from the other side, the leak integrated and fired neuron model, which is fast to simulate but has a lower biological plausibility, even if also recent literature papers demonstrate that Also, simple leak-integrated amplifier are able to predict with a high accuracy the spiking trains of a lot of neurons in the brain, like in the visual cortex also. To solve this compromise, in the world of leak-integrated amplifier neuron model, multidimensional neuron models have been developed, adding the modeling not just of the membrane potential dynamics, but also of other intrinsic currents in the neuron model, which in some way tries to summarize what happened at the subcellular level. In this compromise of biological plausibility and computational load, something else which should be taken into account is also the problem of optimization, as has been said before, because of course also the increasing or decreasing the number of parameters increases the cost of optimization. So in view of simplifying the single neuron of the cerebellum, trying to keep still some biological plausibility in the spiking patterns, but having a reduced computational load to go to large-scale spiking neural networks, we have referred to the family of the generalized leak-integrated amplifier neuron models with the aims to keep the neurophysiological realism with a low computational load, to be able to reproduce generalized features, so not fitting on single traces because we are more focused on the spiking patterns than on the shape of the membrane potential. And then the possibility to generate a cell-specific set of parameters. So parameters in the model should not be associated to one property that we want to reproduce, but to a cell-specific phenotype. So that with a single set of parameters, the neuron is able to generate different spiking patterns depending on the input it receives, which is closer to reality. So we don't have to change the parameters to obtain different behaviors, but it automatically emerges when the neuron receives different inputs. So staying in the family of leak-integrated amplifier neuron models, the model we used and developed is based on 3 state variables, the membrane potential and 2 currents. One is an adaptive current and is coupled with the membrane potential in order to obtain adaptation mechanism and oscillatory membrane potentials, and a spiking triggered current, which is, on the other hand, accounting for faster mechanism like bursting. Spikes are generated stochastically, so with a certain probability if the membrane potential is closer to the threshold. And when the spikes are generated, the state variables are reset. The membrane potential is reset, of course, to the reset value, while the intrinsic current, the polarization-induced current, and the adaptive current are updated to a constant value for the depolarizing current, as you can see on the right, the green one, while the other current is accumulating. So it's accounting for slower processes, and so it's giving adaptation mechanism in the spiking patterns. The model has been developed in Nest using NestML, which was cited yesterday. And based on the analytical solution and relying on experimental data from literature, we could first identify the parameter space in order to obtain, for example, oscillatory membrane potential, and also to keep the parameters within physiological ranges. And then, still based on the analytical solution of the model, we aimed at optimizing the parameters in order to obtain not a fitting of a spiking train or a membrane potential trace, but an input-output relationship. So supposing to stimulate the neuron with different levels of input current, we computed the solution of the neuron with these different levels of input current and minimized the error on the output spike times. After optimization of parameters, for the specifically for the cerebellar Golgi cells, we recorded data adding multiple stimulation values, so not just the ones used during the optimization, but additional input patterns, in order to test not just to generalize the features which were used during the optimization phase, but also to test if the model with those parameters could reproduce other properties like phase reset or resonance with a periodic input spiking pattern. So, for example, as we said before, for the cerebellar Golgi cell, we identified from literature some typical input current values, as you can see on the left, and we minimize the error on the output frequency, and so on the output spiking times. And as we can see from simulating then the neuron in NEST, we could obtain autorhythm at around 10 Hertz. Then a linear input-output relationship. So as you can see on the left, in green we have the target values used in optimization, and of course the model is reproducing the same values with adaptation at the end of the stimulation current step. And following an inhibitory current step, the neuron is giving a rebound burst. So after this optimization phase, we compare the output of the model with experimental data recorded in mice slice, adding also the additional input current steps and input current patterns. So still the response to the increase in the polarizing current steps was maintained, having increasing frequencies of the neuron model with increasing current steps, as you can see on the right, comparing the simulation in black and the experimental data in blue. Of course, we aimed at reproducing the output spike in frequency and not the membrane potential shape, because we are still in the world of integrating fire neurons. Also, looking at the relationship between the stimulation current and the output frequency, we keep linearity and adaptation with reduced spike frequency adaptation in the model with respect to data, due to the fact we have deterioration mechanism in experiments that are not accounted in the model. Then, following spontaneous stimulation, both the neuron and the model are giving spontaneous firing. And after a different hyperpolarizing current steps, both the model and the experiments show the rebound bursts at increasing frequencies. Finally, the last two properties which were added just in the validation phase were phase reset. So both in the experiments and in the simulations, we observed a reset of the spike's phase after an input stimulus. And finally, resonance, so an increased response in the theta band, both in the experiments, even if less pronounced due to the variability of data, and also in the simulations. Then we also tested the response to synaptic inputs, modeling the synapses in the model as conductance-based synapses with alpha-shaped conductance changes. And we used multiple receptors into the neuron in order to be able to differentiate the inputs coming from different neural populations. So, for example, you see there the stimulation of a Golgi cell using an excitatory spiking pattern, the red one, and then an inhibitory burst. They are going to two different receptors, so they are processed differently by the neuron, but still, and they are causing an alpha-shaped change of the conductance for how the synapses are modeled. And you see that in the target neuron, we have, of course, an increased variability of the spiking pattern, and the inhibitory input is causing the rebound bursts. So the same mechanism that we observed due to a current step simulation is occurring during to the spikes going to the inhibitory receptor. And there is also an additional receptor if the input the neuron is receiving to an additional neural population, and setting the parameters you can choose if it's inhibitory or excitatory. Then we generalize this approach to the other neurons in the olivocerebellar circuit, reproducing the input-output, input current and output frequency relationship with different slopes and different adaptation or not adaptation mechanism. Then in case of giving a zero input current or an inhibitory input, the neurons could exhibit subthreshold oscillations, as you see in the granular layer, even if with a higher level of abstraction compared to the experimental data, or pacemaking at different frequency, as you can see in the molecular layer interneurons on the left, and the Purkinje cells and the deep cerebellar nuclei neurons on the right. Then following a hyperpolarizing current step, so following inhibition, neurons like the Purkinje cells and the deep cerebellar nuclei showed rebound bursts, while the other neurons went back to their baseline activity. Finally, additional specific properties which was tested for neurons based on the knowledge from experiments were the burst-pause response in the Purkinje cells, which were intrinsically generated by the neuron thanks to the currents, the polarizing currents and the adapted currents, but we will see more details on this in the afternoon during the tutorial. And finally, also the bursting properties in the inferior olive neurons. Then some oscillation-driven properties in the granular neurons. Also, we observed, we were able to simulate resonance again in the theta band, while in the inferior olive neurons, we could obtain phase reset of subthreshold oscillations, as observed again in the literature data. What happens when we embed these neurons within a spiking neural network? We did this embedding the optimized neurons in the scaffold presented yesterday, and we stimulated the scaffold with stimuli that could be associated with sensory stimuli. For example, we gave a 40 Hz Poisson spiking pattern to the granular layer, which is supposed to simulate like a tone stimulus, and then a burst to the inferior olive neuron, which could be associated to, for example, RPAF stimulation, which is typical in eye-blink conditioning protocols. And we can see on the right that in the Purkinje cells and in the nuclear cell post-stimulus time histogram, the burst pause and burst pauses patterns that were present in single neurons also emerges at network level. So we have the Purkinje cells that are emitting a complex spikes or a burst and then a pause following the inferior olive bursts. And as a consequence, in the nuclear layer, the nuclear cells are pausing and then bursting. And this is enhancing the time accuracy of the response, because the nuclear cells are then going, giving the signal to the motor pathways. So embedding this more realistic single-point neuron into the spiking neural networks can allow us to see how the single neural properties impacts on network dynamics, but also emerges in, when put in closed-loop simulations, emerges in behaviors. But we will see some things of this also in the tutorial this afternoon. Thanks for your attention. If you
Thank you, Lice. There are questions. Understand many, maybe all of us are quite hungry now, would like to go for lunch. If there are no questions, time to talk about all of this in the lunchtime. Thank you.